We are proud to present the EarlyWave Alert Project, which falls under the UN's Sustainable Goal number 9 of Industry, Innovation, and Infrastructure. Hello, my name is Soham, and I am part of the US team.
My name is Hitashma and I'm part of the Nepal team.
Hello, my name is Rishika and I am part of the US team.
Hello, my name is Sarana and I'm part of the Nepal team. The problem is that Nepal has many earthquakes. Since it lies really close to the Indo-Eurasian plate boundary, it has had 1,154 earthquakes in the last century. This has caused more than 9,000 deaths and 23,000 plus injuries.
Why did some of the houses collapse while others didn't? What determines whether a house collapses is the material it is made of and its resonant frequency. Buildings made of brick and concrete are more susceptible to collapse. Most buildings in Nepal are built with brick and concrete. But what is resonant frequency? Resonant frequency is the frequency at which a building has to be pushed around for it to have the greatest chance of collapsing. Taller buildings tend to have a lower resonant frequency.
If the earthquake frequency and the resonant frequency of a building match, then the building has the highest chance of collapsing. If a building's resonant frequency is 0.5 Hz and the earthquake has a frequency of 1 Hz, this building has a lower chance of collapse than a building with a resonant frequency of 1 Hz. Similarly, a building with a resonant frequency of 1.5 Hz has a lower chance of collapsing than a building with a resonant frequency of 1 Hz. The majority of the people did not get adequate warning before the earthquake. As you can see in the brief survey we conducted, most people did not get any warning right before the earthquake was about to hit their building in the 2015 Nepal earthquake. That can be extremely hazardous to all the residents of Nepal because a building could collapse on top of them.
But what is our solution? A personalized sensor for every building. Our solution is an accelerometer-based Arduino setup. It would be set up before the earthquake and would measure the resonant frequency of the building. In the event of an earthquake, it would connect to local seismographic networks and gauge whether the oncoming earthquake poses enough of a risk to warrant an evacuation. In this video, you will see the device take the resonant frequency of this house. It will take this data during an earthquake and compare it to the earthquake data and tell the people in the building whether they need to evacuate or find safety. You have gotten feedback from a scientist here in Massachusetts on our device and our plan. Our solution is aimed at being both affordable and reliable. The systems incorporated by Nepal in 2015 were unreliable because they had many false alarms. Professional grade systems such as Shake Alert in California are reliable but much too expensive.
Many people who were close to us were affected. Countless others lost their lives due to the 2015 Gorkha earthquake. On a personal note, my great-grandmother was stuck in her home because it was shaking so much that she could not leave. We aim to build an affordable, reliable system to reduce future losses and raise awareness for safer buildings.
We aren't stopping yet. We plan to go through with this plan by flying over to Berkeley to test our device on different types of buildings in a simulator. We also plan on collaborating with the Nepali government and other organizations to help deploy our device in Nepal as well as make earthquake education more widespread. Thank you.
Thank you.
Thank you for listening.
Thank you.